easier. But usually, volume is a nice, easy sub it into the formula, off you go. Yeah, but I thought that's potentially what you were doing. But surface area, it's coming. So you're on it. You've already done half the work for yourself. Alrighty. So those who have just joined, hello, hello again. I know I'm a different face. Teacher Jane has a work function, but I'm here. We're doing measurement. So yes, let's get on it. We're under don't stress. I remember to record, so it will be recorded. And like I said, don't stress. As long as you can stay, that's awesome. So thank you for being here. Alrighty, guys. So then what we want to do is we want to figure out the slant height of our cone. Now remember, the slant height is important because if I was really on it, we want to determine the surface area, we need to know what the slant height is. So the slant height is basically exactly what it says, the slanted length of, oh, that was short and sweet, the slanted length of our cone. All right, so we need to go and determine that. And why it was so important that we were told that this is a right cone is because now we see that we've got a right angle triangle here. So we can use Pythagoras to go and determine our slant height. So I'm going to give you like 60 seconds, quickly work out the slant height for me. I will double check that Pythag again. And I'm assuming those 51s, I'm assuming there were decimals there. We're just not writing the decimals. No decimals. So don't worry. No, don't worry. It's just because I'm a bit silly. I used the radius as 25, not 24. Thank you so much. Right. Yes, it is 51 on the dot. I was being silly. All right. So our slant height is the hypotenuse. So hypotenuse squared is equal to 24 squared plus 45 squared. Remember, we should always say Pythag as our reason. Okay. It is a geometric reason. We should give it. We know that we need to give it. And if you need to, if you struggle to visualize the Pythag, remember, just draw out your triangle. So just take your triangle out of your diagram, draw it out for yourself, which maybe is what I should have done because I can't read my own handwriting. And then you can go and determine what you need. So yes, once we apply all of that, we get our slant height is 51 centimeters. And like I said, we now need this if we want to go and determine our total surface area. Right, so total surface area is pi r squared plus pi rs. Just gonna grab that formula for us and pop it down here where we need it. And so again, I'm going to give you 30 seconds to go work out your total surface area. I was on it, so let's see if we all agree. Right, give me a thumbs up if we agree. That's the total surface area. Sorry, I said agree. Do we all agree with was 5,654,87 centimeters squared? Give me a thumbs up if we're all in agreement with that. No one agrees. Okay. Right, well, it is indeed 5,654,87 centimeters squared. That is your total surface area. So when it comes to shapes like cones, pyramids, and spheres, total surface area becomes a little bit harder because we have to know the formula. It's not a case like when we have, I don't know, a rectangular prism where we can break it up to the into the net and we have shapes that we then know how to work with. If I broke this cone up into its net, that curved surface is going to be a weird like situation like that. And then we have our circular base. We don't know a formula to work out that weird curved looking pizza slice thing. And so this is why it's so important that we do know our formulas and that we can pick out our formulas. Now, with that being said, we are not expecting you to learn the formulas off by heart. Usually for these formulas, we do give them to you, but we will just say V equals. We won't be nice like this and say volume of cone equals. We just say V equals, TSA equals, and we expect you to know which is which. Generally speaking, it's kind of easy to pick out. So the second there's a pi, we automatically know there's some circle involved, so it wouldn't be a pyramid, for example. And then when it comes to spheres and stuff, we then just have to be able to differentiate between cones and spheres. But you are expected to know your formulas to be able to kind of pick them out. Okay, so I've just made it a bit smaller so you can screenshot everything there. And then we're going to have a look at the next one. Okay. And remember, guys, if you do have questions at any point, please just ask. You can raise your hand. You can put it in the chat. I've got the chat open. I can see. Yeah, just let me know. Alrighty, so feel like no, okay. If we have a look at our next question, I feel like we've skipped question 2, hence why I had a bit of a panic moment, but we're all good. I think we just didn't have a question 2 here. Just to make sure from teacher Jane. Yeah, okay. So if we have a look at this next question, we now have a sphere that has a radius of 21 and we want to calculate the volume and the surface area. Again, you've got your formulas on the side there. I'm going to give you 3 minutes. Let's calculate the volume and the surface area of the sphere with a radius of 21 centimeters quickly. Again, pop your answers in the chat, double check yourselves with each other, ask if you're unsure about anything, but let's give it a try. Right, give me a thumbs up if we are done. Okay, let's have a look-see. So in this case, we were given the radius. What would we do if we were given the diameter? So if I told you that the diameter was 21, how would we deal with that? Because obviously our formulas don't rely or don't use diameter. Okay, good. So, and I know it seems like such a silly question, but sometimes, not to throw you off, but sometimes we will give you the diameter instead of the radius, and we need to know how to deal with that. Right, so volume is equal to 4/3, and then apparently I write 3. So 4/3 pi r cubed, so 21 cubed. And again, we know that that would be the formula because of that cubes and because of the pi. But once we chuck that into our calculator, 38,792,39 centimeters cubed. And then when it comes to the total surface area, again, we've got our formula. That is equal to 4 pi r squared, so 21 squared, which is equal to 5,541.77 centimeters squared. And that's it. Okay, so once you have your formulas, things become a whole lot easier. All right, I'll just wait for you to screenshot this too, and then we'll have a look at question 4. Right. So if we have a look at question 4, we now have a hemisphere. What is a hemisphere? Or hemisphere, however you want to say it. Okay, good. So it's half a sphere. So much like anything, if we were to cut it in half, we just need to be mindful of what that means. Now, I don't know how well I'm going to draw this hemisphere, but we're just going to roll with it. It was average. Okay, so there's my hemisphere, and we're told that it's got a radius of 12 centimeters. So there's a couple things we now need to bear in mind. When I want to work out the volume, okay, and just a reminder, a volume of a sphere is 4/3 pi r cubed. When we now want to work out the volume of a hemisphere, we would need to divide that by 2 because we only want 1/2 of that spherical object. And when it comes into the total surface area of a full sphere, we have got 4 pi r squared. Now, what we need to bear in mind is that that is for the whole sphere, okay? If we now halve it, we're only getting the curved halves area. So we would only be getting sort of this section's area over there. We need to also remember that because we've now chopped it in half, we actually also need to think about that circular base at the bottom. So once I've chopped my sphere in half, I now have that circular base at the bottom that I need to consider as well when I do my total surface area. Right, are we feeling good about giving this a try? Give me a thumbs up if we think we can give this a try. I'm happy to do it with you, but if we're feeling good, you might as well give it a bash. A thumbs up if you're confident you can do this. One person confident. Okay. Right, let's do it together then. So volume, again, like I said earlier, volume is generally the easier of the calculations. We now want of our hemisphere. So we are going to take the volume of our sphere, 4/3 pi r cubed, and we are going to then halve it. Now you are more than welcome to obviously do all your calculations in one go. You can also find your answer first and then divide it by 2. It is completely up to you, whatever you're comfortable with. So once we substitute in, we've got a half, 4/3 pi. My radius is 12 squared. And we end up with a volume of, I think you just swapped your numbers around, so don't panic. 3,619, so 3,619,11 centimeters cubed. That's the volume of half of my sphere. Now, when we get to the total surface area, we need to consider that curved surface as well as the circular base. So we are going to have to work out the area of the sphere surface, but then we are going to have to halve it so that we just get 1/2 of that curve. And then we're also going to have to add the area of the circular base. Again, you can do it all in one step. You can do it step by step if you want to. It is entirely up to you. You decide what you want to do. But we get 1/2 4 pi times my radius. I keep running to 21. 12 squared plus the circular base, which is pi r squared. We put that all into our calculator, or again, do it step by step, that's fine. 1,357,17 centimeters squared. So when we start to chop up shapes, when we start to put shapes into other shapes, when we start to consider shaded areas, all of that sort of stuff, be mindful of what it is that you need to subtract. Be mindful of, excuse me, if we like cut a shape in half, like what we did here, be mindful of what that now does. For example, creating that whole new face that we now need to consider in terms of our total surface area. All right. Okay, are we ready to step it up a little bit? I'm just going to wait here for you guys to screenshot. Okay, right, just because I don't want to, I don't want to grab anything. All right, question 7. We have got the roof of the canvas tent is in the shape of a right pyramid having a perpendicular height of 0.8 meters on a square base. The length of one side of the base is 3 meters. So we've got that there. And there's a bunch of things we want to calculate, but I would like to give us the formulas. And I really thought I just had them quick sticks for myself, but obviously I don't, because why on earth would I make my life easy? Right. Volume is equal to 1/3 area of your base times the height of your pyramid. And then obviously when it comes to your total surface area, you will have, in this case, 4 identical triangular faces. And then potentially the square base at the bottom. Obviously, we will decide what we need. Okay. So the first question is asking us to calculate the length of AH. So AH is that slanted height over there. So now we need to decide, well, what information do we actually have, and can we go and determine that? Now, if you have a look, that would potentially be created or be part of this red right angle triangle that I've kind of drawn here. So what we want to do is we want to decide, do we actually have all of the lengths that I would need in order to potentially use Pythagoras? We know that the height is 0.8 meters, and we were told that this whole side length is 3 meters. Now, because this is a square-based pyramid, and from the apex down to that perpendicular height or down to the base is a right angle, it's actually also cutting or sitting smack bang in the middle of that square. And so what that means is that this length from the middle to B is half of 3 meters, so 1,5 meters. So we do actually have enough information to calculate the length of AH. So I will put there on the chat already that we've calculated AH to be 1,7 meters, which is 100% correct. We would use our Pythag, so AB squared is equal to 0,8 squared plus 1,5 squared. Again, don't forget Pythagoras your reason. I know it seems silly, but we will take off a mark. And we get that, why am I saying AB? AH. We get that AH is equal to 1,7 meters. Right, once we have our slant height, obviously that's quite useful for us because when it comes to working out the surface area, very useful. So now in the next question, it's asking, calculate the surface area of the roof. Now, I hope you can all agree with me that we are not going to include the square base to this pyramid. That is not part of my total surface area. The only thing I need to calculate is the area of these triangular faces to my pyramid. Again, because it's a square-based pyramid, all of those triangles will be identical. And to work out the area of a triangle, we need the base and the height. We know that each of these base lengths are 3 meters, and we've just worked out that the slant height of this triangular face is the 1,7 meters. So we are going to get 4 identical triangles with areas half the base of 3 times the height of 1,7. And so we get nice 10,2 meters squared. Right. So always just look out for, particularly when you've got like compound shapes like this, where there's multiple shapes together, just be mindful of not including sides that maybe aren't exposed. So like the square base here, or I don't know if there was an opening, we wouldn't consider one of those sides, etc., etc. So just be mindful of that when you do questions like this. Right, 713 says if the height of the walls, can I make it, is that fine? Is that still, can everyone still see that? I'm actually also just going to make my own choice here. Right. So 7.1.3 says if the height of the walls of the tent is 2,1 meters, so basically this bit here, 2,1 meters, calculate the total amount of canvas required to make the tent if the floor is excluded. So we're not going to have canvas on the floor, and we now need the total surface area. So what do we now need to add to the sort of roof surface area? What do we now need to calculate to figure out the total surface area of the whole tent? Nice. Okay, so we've got 4 square faces here that we now need to add on. So we've already got the area of our roof. That's fine. So total surface area of our walls is 4 squares of 3 by 2,1 meters, which gives me of my walls exactly 25,2 meters squared. And so therefore the total surface area of the tent, including the roof, is the 25,2 plus the 10,2 meters squared. And so now we have, let's just write it here, that the total surface area is 35,4 meters squared. Right. And again, just think logically about what is included, what isn't included when you go and do your calculations. I'm just going to do that so we can screenshot everything, and then I will move on to the next one. Alrighty, so let's have a look at 7.2. A metal ball has a radius of 8 millimeters. So because it's a ball, we know we're dealing with a sphere, blah, blah, blah. And we have a radius of 8 millimeters. Calculate the total volume of metal used to make this ball, correct to 2 decimal places. All right, let's first try that one, and then we'll have a look at the next one. I would like the volume of metal needed to make this ball, 2 decimal places. Does anyone need me to write the formula down again? Okay, I put the formula there just in case you did need it. You do have it, but I just put it there. Let me give you 1 more minute and then we'll have a look at what the volume is. And again, you're welcome to put it in the chat so that we can check each other and check ourselves. Okay, let's see. So volume is equal to 4/3 pi r, which is 8 cubed. And so we get 2,144,66 millimeters cubed. And grade 11 is just that we're aware because it specifically said, oh gosh, specifically said 2 decimal places. If you round off incorrectly, we will deduct a mark. When we are specific about how we want our rounding, you will lose marks if you don't do it. Right, so 7.2 now says if the radius of the ball is doubled, write down the ratio of the new volume to the original volume. Okay, now technically we shouldn't even need to calculate a new ratio or anything like that. We should hopefully understand what's going to happen. Now, if we were to double that radius, okay, so the radius is currently 8. If I doubled it, I would obviously have 16. But what we now need to bear in mind is that by doubling the radius, when we now look at the volume formula, okay, no, it's not what I wanted to write, r cubed, we need to think about the fact that r is being cubed. Okay, so the answer is going to be 8 times larger. Abu, can you explain why? Anyone? I know I picked on Abu, but can anyone explain why it would be 8 times larger? Okay, so exactly, because the volume formula has a cube, an r cubed, if we double one dimension, then obviously it would double. If we double 2 dimensions, it would double twice, so times 4. And if we double 3 dimensions, which is what we're doing here because it's r cubed, we are doubling thrice, which is times 8. And so what we end up with is that the new volume is 8 times larger than the original volume. Now, grade 11s, obviously, if you didn't recognize that pattern, if you hadn't learned that pattern, often people don't necessarily teach us because it is considered like a problem-solving complex question, more complex. You could just go work it out. So you could just now take your doubled radius, you could sub it back into a volume formula, and you could get the new volume and work out the ratio between that and the original. But it is useful to know that when we do double, triple, quadruple, whatever dimensions in our 3D shapes, it does have this sort of corresponding effect in terms of surface area and volume. So if we were looking at the surface area, that would be 4 pi r squared. And because we're working with because we're working with r squared and we're doubling it, it would be 2 to the power 2. So the surface area would be 4 times bigger because we've taken 2 radii, r squared, and we've doubled each of them. And if you double and you double, you're timesing by 4. So always just think about what it means in terms of the number of dimensions you are doubling, tripling, whatever, and that then has a knock-on effect with the new total surface area or the new volume for your shape that you're working with. Right, I'm just going to wait there in case you want a screenshot. There is one more question, but actually, no, we'll fit it in. I wasn't sure if we would fit it in, but I think we might. Okay, so 7.2.3 says, I'm just going to cover this up so that we have space. So it says, you would like this ball to be silver plated to a thickness of 1 millimeter. What is the volume of silver required? Give your answer correct to 2 decimal places. Okay, so I'm going to give you a second to think about it. I'm going to give you a second to try and work it out, and then we'll have a look. I'm going to give you, I'm going to give you a second. I'm going to give you 2 or 3 minutes. We now want to add 1 millimeter thickness all the way around this metal ball in order to silver plate it. So let's think about what that means and what that means in terms of the volume and our calculations. I'm going to give you 2 or 3 minutes, and then we'll have a look. What's wrong? Okay, the yaw is saying we're not too sure. So let's have a look. So what we have, remember, is our spherical ball. Okay, that's nice. That's all great. And we need to bear in mind that the radius was 8 millimeters. What we're now wanting to do is we're wanting to add on the silver plating. So we're wanting to add an extra layer of thickness to the sphere. Okay, oh gosh, you get the picture. And we were told that it is going to be 1 millimeter thick. So this thickness all the way around here is 1 millimeter. That's trying to be a millimeter, but it's failed. Okay. So my first question to you is, if I now consider the blue sphere that is now 1 millimeter thicker, what we now have is a situation where we've got 1 millimeter extra on either side. And so that means that my new radius is 9 millimeters. And so what I can do is I can go and work out the volume of the slightly bigger sphere, subtract the volume of the original metal ball, and then what I'm left with is just that thin silver plating volume around the outside. And so that's what we need to do here. And that's what I was saying earlier. Whenever we need to think about shapes that are being compounded, so multiple shapes together, whenever we're thinking about shapes inside another shape, 99% of the time, it's a subtraction that we're going to have to do. So if we work out the volume, including our silver plating, we're increasing our radius to 9 millimeters. And so that's going to give us 3053,63 millimeters cubed. And then what we want to do is, because we just want that like sort of thin silver plating blue bit, we have to subtract the metal ball. So what we're going to do is we're going to take the volume of silver plating. In order to get that, we're going to take the volume of our original, of the original ball plus the silver minus just the volume of the ball. So the volume of the ball plus the silver is what we just worked out, the 3053,63. We're going to minus that original volume that we got earlier of 2144,66. And that difference tells me that the volume of silver plating needed is 908,97 millimeters. Okay, too many things trying to be m's, millimeters cubed. And so that value there is giving me just that thin blue plating of silver around the outside of that spherical object. So it's really important to remember, like I said, whenever we're dealing with compound shapes and shapes within other shapes, subtraction is the name of the game. And usually, especially if you're feeling stuck, work out the volume of the bigger shape, subtract the volume of the smaller shape. 99% of the time, that's what you need to do. Okay, so let's just, yeah, that was all your information. Let's just do that so you can screenshot everything. Right, and then we're going to have a look at one that's it's very much a test exam type question. And so if we can do this next one, then we should be pretty set when it comes to measurement in terms of our assessments. Okay. No, apparently that's going to happen. Right, I just want to grab our formulas. I'm not going back and forth. All right, Jabulani sells ice cream cones. Each ice cream is approximated as a perfect cone with a hemisphere on top, with a radius of 2 centimeters and an overall height of 16 centimeters, as shown below. So we've got those two images there. We can see the ice cream cone. We can see our dimensions given to us, and important, overall height. So basically from the top of your ice cream scoop all the way down to the cone, that whole thing is 16 centimeters. Before we even get into a question, how tall is the hemisphere of ice cream? Think about where I've drawn that blue line. How tall is that? Why, Abu? Why is it 2 centimeters? Which seems stingy. Jabulani needs to think about how much ice cream he's giving people. Yeah, that seems stingy. Anyways, I digress. Yes, it's the radius. So because the radius is measured from the center out to any point on the circumference of my hemisphere, this height of the ice cream blob is 2 centimeters. So how tall does that make just the cone? Nice. Okay, 14 centimeters. Excellent. Well done. Okay, so now we're going to look at our questions. Assuming that the cone is completely full of ice cream. Okay, I judged Abulani a little bit quickly. Apparently he's filling the cone, so I take it all back. 2 centimeters I'm okay with. Assuming that the cone is completely full of ice cream, determine the total volume of the ice cream. So total volume, we're needing all of the ice cream in the cone, so the volume of the cone, plus the volume of the hemisphere on top. So again, I'm going to give you 3 minutes. Let's go work out the volume of ice cream that Jabulani is serving his customers. Okay, let's have a seat. So again, if you are comfortable doing everything all in one step, please by all means go for it. We need the volume of our cone, which is 1/3 pi. The radius of the cone is 2 squared times the height of the cone, which we worked out to be 14. And then we want to add the volume of our hemisphere, which is 1/2 4/3 pi r, which is also 2 cubed. Type that all into your calculator and we get a total 75,40 centimeters cubed. It is absolutely fine to do it the way I've done it with everything all in one step. You don't necessarily have to work out that it's 58,64 plus 16,76. You can, it's fine. But what we are looking for when we mark these sorts of questions is have you substituted into the correct formulas and then your answer. It's okay to do it all in one step. Right, it then says in 8.2, Jabulani likes to have a layer of ice cream sauce on his ice cream. Assuming that the chocolate sauce is exactly 2 centimeters thick, not 2 centimeters, 2 millimeters thick, and that it covers all and only the ice cream on the outside of the cone, determine the volume of chocolate sauce which Jabulani will need to coat 50 ice creams. Okay, so I'm just going to move this up so that we've got some space. There's a couple things here that we now need to just be mindful of when we go and answer this question. Right, so the chocolate sauce is only covering the outside. So my chocolate sauce is basically only covering this hemisphere of our ice cream. Because it's 2 millimeters thick, essentially what I'm doing is we know that this radius is 2 centimeters, but now we're adding on an extra 2 millimeters, so 2,2. We need to figure out how much chocolate covering or chocolate coating we need. So we're going to work out the volume of this hemisphere with the extra 2 millimeters. But then what we must remember is we're working out a solid hemisphere. We would need to subtract the ice cream inside. So we would need to take the volume of the ice cream. I don't know why I put a plus in the middle there. Ice cream plus chocolate. And then we'd have to minus the volume of just the ice cream. And that will give us the volume of just the chocolate. And then once we have the volume of just the chocolate for one cone, we would just times that by 50. Now we already have the volume of the ice cream. If you've done it separately in 8.1, you have that information. And so now all we need to do is work out the volume of the ice cream plus the chocolate. So that's going to give me half, because it's the hemisphere, 4 over 3, pi my radius, which is 2,2 squared, minus the volume of my ice cream, which was the 16,76 in the question before, or you just put it into the formula again. And that's going to give me the volume of just the chocolate, like I said. And so the volume of chocolate that we're using is 5,54 centimeters cubed. Now I want for 50 ice cream, so I times that answer, because that's just for one, times that answer by 50, and I get that you would need 277,24 centimeters cubed of chocolate. And then what would be a nice sort of follow-on question or an add-on question to this is they could have asked you for this in milliliters. And then just remember that 1 centimeter cubed is equal to 1 milliliter. So this is 277,24 milliliters. Like I say, could have asked you, they didn't ask you in this case, just a nice sort of add-on question to have there. Right, I will let you screenshot everything in a second. Let's just have a look at this last one. Dorothy also has an ice cream, which is the same as Jabulani's, except that her ice cream's overall height and radius are larger than Jabulani's by a factor of 1.5. Write down the ratio of Dorothy's ice cream's volume to Jabulani's ice cream's volume. So remember, this is what we've just spoken about. Her factor that we're increasing by is 1.5. And because we're talking about volume, we're talking about 3 dimensions that are being increased by 1.5. So we would cube that. And we are comparing that to Jabulani's 1. Why 1? Well, because I'm starting off at my starting point of Jabulani's volume, and I'm timesing that by 1.5. So 1 is sort of my original volume, my starting point, and then I increase it by a factor. Now, what this ends up being is 27 over 8 to 1. And then because we don't want fractions in a ratio, we never want fractions in a ratio, I'm just going to times both sides by 8, and I get that the ratio is 27 to 8. So this just goes back to the discussion we had earlier in terms of if we are tripling, doubling, 1.5 times in a dimension, that needs to then factor into the dimensions I'm multiplying for the volume. Again, definitely a more complex question, but again, just think about how many dimensions it is you're increasing and by what factor. All right. Oh gosh, sorry. So let's screenshot those first two, and then I'll scroll down to the next one. So guys, this last one, very much a nice sort of test exam type question, where there's multiple volumes, there's subtraction of volumes, there's ratios, etc., etc. Oh, I see your question. I'm just thinking it doesn't really affect the answer, because even if it was including the source, we're still only increasing by 1.5. So we're not having to add an extra anything, because the whole, because it says the overall height and radius are larger by 1.5. So it's taking into account everything. So we're not really needing to stress about whether or not there is the chocolate sauce, because just because of the fact that they said overall, including everything. Does that make sense? Okay. Oh, no, it's a good question. And often, like, those sorts of things are really important to consider. So good question. Right, so there's the last one for you guys to screenshot. It is 6:30, so you're more than welcome to go. I mean, you are going to go. But thank you so much, grade 11s. Teacher Jane will be with you obviously from next week Tuesday again. And if you are writing exams, good luck. If you're getting ready for exams, good luck. It is the last few days, I think, for most of you. So I hope they go well and your studying is going well. Bye, grade 11s. Have an awesome evening.